Hello, students! Have you ever looked into a curved mirror and wondered how we can predict exactly what the image will look like? Well, today, we're going to master the tool that lets us do just that, ray diagrams. We will also learn the essential rules for measurement, known as the sign convention, which is the key to solving any calculation involving mirrors. But first, let's think about something you see almost every day, a new, shiny spoon. If you look at the side that holds the soup, the concave side, you see one type of image, and it's often upside down, isn't it? But then if you flip it over to the bulging, convex side, you see a completely different image, always upright and smaller. That's because a simple spoon is acting like two different types of spherical mirrors. So, the question is, how do we scientifically predict what that image will be, where it will form, how big it will be, all without even having the mirror in our hands? For that, we need a reliable tool. And in optics, that amazing tool is a simple drawing technique called the ray diagram. So what exactly is a ray diagram? You can think of it as a map that traces the path of light. We follow the rays of light coming from an object, see how they bounce off the mirror, and then find the exact point where these reflected rays meet. That intersection point, that's where the image is formed. And the best part is, we only need to accurately draw two of these rays to find our answer. Okay, so let's get into our toolkit. You see, an object gives off countless light rays in all directions. But thankfully, we don't need to draw all of them. That would be impossible. Instead, physics gives us a special toolkit of 4 very simple, very predictable rays. If you can just master any 2 of these 4, you can construct any ray diagram perfectly. Let's start with our first reliable ray. Imagine a ray of light that is traveling parallel to the principal axis. Now, look at the concave mirror on the left. When this ray hits the mirror, it reflects and will always pass through the principal focus F. Now, for the convex mirror on the right, the ray reflects outwards. You see, it diverges. But if you trace this reflected ray backwards with a dotted line, it will appear to come from the focus point located behind the mirror. Our second ray is simply the exact reverse of the first one. It's a beautiful symmetry, really. For the concave mirror, if a ray passes through the focus before it hits the mirror, it will reflect and travel out parallel to the principal axis. And for a convex mirror, if we aim a ray towards the focus behind the mirror, it will also reflect and travel out parallel to the principal axis. See? Just the opposite of Rule 1. Now, this third ray is probably the easiest one to remember. Any ray of light that passes through the center of curvature, C, is special. It hits the mirror straight on, at a 90-degree angle. Because of this, it simply reflects and travels right back along the same path it came from. This works the same for both concave and convex mirrors. It just retraces its path. And our fourth and final ray is one that strikes the mirror directly at its center point, the pole, P. This one follows the basic law of reflection that you've already learned. It's like bouncing a ball off the floor. The principal axis here acts as the normal, so the angle of incidence is always equal to the angle of reflection. Very straightforward. So now that we have our toolkit of 4 special rays, let's start building. We will now use any 2 of these rays to construct the images formed by a concave mirror when we place an object at different positions. Okay, case number 1. We place the object exactly at the center of curvature, C. Let's draw our first ray parallel to the axis. After reflection, it passes through the focus F. For our second ray, let's draw it passing through F. After reflection, it becomes parallel. Now look carefully. Where do they intersect? They meet exactly at C. This tells us 3 things. The image is real, it's inverted, and it is the exact same size as the object. Right, now let's see what happens when we move the object a bit closer. We'll place it somewhere between C and F. Again, let's draw our 2 rays. One parallel ray reflects through F, and one ray through F reflects parallel. Now, notice where the intersection point is. Has it moved? Yes! The rays now meet beyond C, so the image formed is still real and inverted, but now it is clearly bigger, it is enlarged. Okay, now for a very special case. This is how a shaving mirror or a dentist's mirror works. We place the object very close to the mirror, between the pole P and the focus F. Now, when we draw our rays, look what happens. After reflection, the rays spread out, they diverge. They will never actually meet in front of the mirror. So what do? We have to extend the reflected rays backwards, behind the mirror, using a dotted line. And where these imaginary lines meet, that is where we find our image. It is a virtual erect and enlarged image. After looking at all those different cases for a concave mirror, I have some good news for you. When we talk about convex mirrors, things get much, much simpler. There is really only one main result to remember. Here is the most important takeaway for convex mirrors. It does not matter where you place the object in front of it. The image that is formed will always have the same three properties. It will always be virtual, meaning it's formed behind the mirror. It will always be erect, which means upright, and it will always be diminished or smaller than the object. This is exactly why they're used as rear-view mirrors in cars. They always show an upright image and give a wider view. So, ray diagrams are fantastic, aren't they? They give us the qualities of the image. Is it real or virtual, inverted or erect? But to do precise calculations using the mirror formula, a drawing is not enough. We need numbers. And for our numbers to be correct, we need a consistent system for our measurements. To make sure that our calculations are always correct and consistent, so that a student in India and a student in another country get the exact same answer for the same problem, we all agree to follow a standard set of rules. This system is called the New Cartesian Sign Convention. It's very logical, so let's break it down. The easiest way to understand this is to imagine placing the mirror on a graph paper. We treat the pole of the mirror, P, as the origin, the point 0, 0. The principal axis becomes our x-axis, and a vertical line through the pole becomes our y-axis. The most important rule to remember is this. All distances are measured from the pole. The pole is our starting point for everything. And the rules are exactly like the ones you learned in coordinate geometry and maths. It's very simple. Any distance measured to the left of the pole is taken as negative. Any distance measured to the right is positive. For heights, anything measured upwards, above the principal axis, is positive. And anything measured downwards is negative. That's it. 4 simple rules. Now here are a few key points that will help you avoid very common mistakes in your exams. First, since we always place the object on the left side of the mirror, the object distance, u, is always negative. Second, real images are inverted, so their height, h', is negative. Third, a concave mirror's focus is on the left, so its focal length, f, is negative. And finally, a convex mirror's focus is behind the mirror, on the right, so its focal length is positive. Remember these points and your calculations will be much easier. All right, we have covered a lot of ground today. We have learned how to draw the images, and we've learned the rules for measuring them. So let's quickly summarize the key takeaways. This is your foundation for solving any numerical problem related to spherical mirrors. Think of this as your checklist. First, master at least 2 of the 4 standard rays. Second, understand the big difference between real and virtual images. Real images are formed where rays actually intersect and are always inverted. Virtual images are formed where rays appear to come from and are always erect. And third, always apply the sign convention, with the pole as your origin. Left is negative, right is positive. Up is positive, down is negative. So, with these 2 powerful tools, the skill of drawing ray diagrams and the logic of the sign convention, you are now fully prepared for the next step. You are ready to apply the mirror formula to calculate the precise position, size, and nature of any image. You have built a strong foundation, and you are ready for the numericals.